Welcome. So this is the video on the first examples on internal forces, right? So the process is simple. Free body diagram. We make the cut and we identify our internal forces. Now, depending on the number of variables you have in each half, you make a decision, right? You have to choose the half in which you have enough equations to solve for your unknowns, right? You can find your reactions first, right? Of course, but in some cases there is not even need to calculate reactions, right? So let's take a look. So in this example, we have to find the internal normal force, the shear force in the bending moment at point C. So here is my point C, right? And we have to find the internal forces caused by these loads. So I have my figure here. I make it a cut, and I end up having these two halves. I label my unknowns. In this case, the reaction. I have a fixed support at point A, which means that I have these three reactions: reaction in X, in Y, and a moment reaction. I remember I write here my convention of signs. Very important, right? Very important to have my convention of signs. And this is how we're going to do it. We have to draw the internal forces on these two halves of the beam, right? Let me see. Let me just probably use green color. So if I am going to deal with or work on this half first, right, the one that I'm drawing or shading in green, I have to find that the same side on my convention of signs. So that this side, the one that I just shaded in green, is this side here, right? This one. So I have to place my normal forces following this convention of signs on that side. So I do that and I obtain these forces. Now I work on the other side, right? I'm going to shade the side that we're going to work on. And I have to work on this side. Now on top, I'm working on my convention. I have to draw the forces in the way they are drawn, right? So the axial force this way, moment this way, and shear force this way. So I place the forces there. So this is how internal forces are drawn. Right? Very important to follow the convention, right? And then this is one very efficient way to do it. Now I take a look at my my system. I could have obtained the reactions as a first step, but sometimes it's not needed, right? So I take a look at the two halves, right? I label my internal forces, right? And now I realize that I'm obscuring the names, right? So let me remove the shading. And you can see that I have labeled my internal forces as moment at C, normal force at C, and shear force at C. And I have the same forces on the other side with opposite sign, right? Let me just remove here the, right, for some reason. There you go. For some reason I have here. Well, anyway. So the point is that I take a look at the two halves, right? And I have to choose the half that allows me to get the internal forces without the need of calculating anything else. So to solve for the internal forces, we have three equilibrium equations, right? So which half of the beam to choose? Now, if I choose the left-hand side, I have 6 unknowns and only 3 equations. And if I choose the right-hand side, I have 3 unknowns and 3 equilibrium equations. So the choice is clear. I have to choose the right-hand side, right? And I can start working on my equilibrium equations. So the next step is to apply the equilibrium equations. I choose the right-hand side and I add the forces in X, right? Everything that goes to the right is positive, right? And then I start. So I have a normal force right, going to the left. You see this guy going to the left, and then I have a horizontal component of the 25 kilonewton force, 25 cosine of 30 degrees going positive, so plus sign, and then that's equal to 0. One equation, one unknown, and the normal force is equal to 21.7 kilonewtons. I apply equilibrium forces in y equal to 0, right? Everything that goes up is positive, and I do shear BC, right? VC going up positive. The 25 kilonewton component goes down, this guy. So it's minus 25 sine of 30 degrees. And then I have a force of 50 kilonewtons that goes down. So minus 50 kilonewtons equal to 0. So I solve for VC, one equation, one unknown, and I get VC equal to 62.5 kilonewtons. And there is one more equation to apply. So sum of moments at C equal to 0, counterclockwise positive. I add my clockwise MC as negative, right? The 50 kilonewtons is doing clockwise moment about point C. So it's negative 50 times 3 meters, right? And then the 25 kilonewton force, it's doing clockwise rotation as well. So negative 25 sine of 30 times 6 meters, right? Times 6 meters. So these 3 plus 3 meters, 6 meters equal to 0. So the moment at C is equal to minus 25 kilonewton meter. The positive signs I got in the normal force and the shear force. They mean that the assumed senses of the forces are fine, and the assumed sense for the moment, it goes onto the other way. So right, so the forces are like this, right? So normal force is positive that way, the shear force that I found is positive that way, and the moment goes this way, right? Those are the conclusions. Those are the conclusions I found with my normal forces. So this is the end of this particular example, right? Interesting things that we did here. We didn't even need to calculate the reactions, right? We choose wisely our half, and then we didn't have to calculate any reactions, right? So those are the things that we did. On to the next example, right? On to the next example, which is about calculation of internal forces again. So we have to find the internal normal force, right? The shear force and the bending moment at points C and V in the beam. Actually, this example will only deal with the normal forces at point C, because we want to illustrate what happens when you cut in the middle of some distributed load, such as this one, right? So you have to do a special consideration there to get the right forces, right? So I have my example here, right? Let me see. And then in this case, we are going to calculate the reactions first, right? In this case, it's beneficial to calculate reactions. So let me take a look. I have a pin at node A, and I have a roller in this particular point. So my two reactions are two reactions at A in X and Y, and then one reaction vertically in B. And then I went ahead and divided the distributed force into a rectangle here and a triangle. So let me shade it for you. So we have to, same as we did with our calculation of reactions, we have to divide our loads into simpler shapes, right? So in this figure, we have already calculated the forces on the shapes, right? In the triangle, there is a force of 150 pounds, and in the rectangle there is a force of 600 pounds. You can double check these numbers, right? It's just the area. It's just the area of the shapes. For example, this the triangle is 20, right? Here is this height of 20 pounds per foot. So it is the height 20 times the base of the triangle, which is 50 feet, and then divided by 2, right? And then that gives you 150 pounds. Whereas for the rectangle is the base of the rectangle, which is 50 feet, times the height of that rectangle is 15 times 40 gives you 600 pounds. So these are the forces I got, and the positions of the forces are based on the centroids of a triangle, which is 15 divided by 3 gives you 5 feet, and then half of 15 gives you 7.5 feet. So these are the equivalent forces, right? There is one more force here in the right hand side. Don't forget about that force to calculate reactions. So we calculate reactions, sum of forces in X equal to 0. Everything that goes to the right is positive. I have a force, let me use another different color. Let me use red. So reaction at X at A, positive, and then a component of the 690 force, right? The component goes to the left, so it's negative. 690 sine of the angle, which is 5/13, and then there are no more forces in X, so this is equal to 0. The reaction at X is equal to 265 pounds, right? So this is my first reaction. Then the next equilibrium equation, sum of forces in Y equal to 0, everything that goes up is positive. I have reaction at A in Y positive going up, reaction at B in Y positive going up, minus 150 coming from the triangle, coming down, 600 coming down from the rectangle, and a vertical component of 690 sine of the angle coming down gives me 0, which means that this was the cosine of the angle, right? On the 690, and this is the sine of the angle. I think I say sine for that upper component, the X component. And then I have an equation, two unknowns. I have to wait for my moment equation. I choose the point A, and I have one moment coming from the triangle that causes clockwise moment, so it's negative. I have the force from the rectangle, causes clockwise moment, so negative again, times the moment arm. And then positive moment from RVY times 15 feet, moment arm. And then I have no moment from the horizontal component of 690, but I do have clockwise moment from the 690 vertical reaction. So it's minus 690 sine of the angle times the moment arm, which is 25 feet, and I have only one unknown, which I solve, and RVY is 1412 pounds, and the reaction at A in Y is minus 25, which means that this reaction actually is acting down, right? So I have my three reactions, right? One reaction, two reaction, three reactions with my three equilibrium equations. So now I have my three reactions. I just write them on the figure, and then I'm going to break my shape at point C. So I draw a line over there, right? And I wonder which half I can choose to make things easier on myself. So just for the to illustrate the point on how to deal with distributed loads when I cut through them, I'm going to work with this half, right? I'm going to work with the left hand side, and then I'm going to draw my convention, or I could draw my convention of signs, right? That's not a problem. So positive senses, right? I believe, right, I'm forgetting my own convention of signs. doing here? Have to go backward. Here. So my shear force goes up and down, and my moment goes this way and this way. So in this half, my internal forces are going to be or follow this orientation, right? These are my normal forces on that point. So I have now to solve the system again, because I have to use my equilibrium equations again, right, on the left hand side that I chose. And I have to add again forces in x equal to 0, forces in y equal to 0, and sum of moments at any point equal to 0 as well. You may argue that I already did this when I calculate reactions, but I did that before I had cut my distributed load. And now I have, once I cut it, I have different loads, right? In fact, take a look, right? Take a look. Now, if I want to divide my load into, again, a rectangle, I think it was, I used the green color for the rectangle and I use a red color for the triangle, right? In fact, I am not sure about this distance, which I am calling x. And then I'm not sure about this distance, which I'm calling 60 minus x, because the previous relationships were made for 15 feet. And now I have to recalculate those ratios for 12 feet. So it's a similar triangle calculation they have to make. But I want you to realize and to agree with me that in the past was easy, right? I had a trapezoid, which I knew that if this was 15, right, this was 40, sorry, and this was 20. But now that I have the same trapezoid, or the same ratio of trapezoid, for a distance of 12, I am not quite sure about, I know that this is 60, but I'm not quite sure about this distance and this distance. This is x and this is 60 minus x. So I have to do a bit of similar triangles before I deal with those forces in the left hand side. So, right, my new rectangle and my new triangle that look like this, and right, my forces have to be based on the new geometry, right? So in fact, I have a note here that says, to be able to determine the force at point C, I must find the forces in the side of the beam I chose in the left hand side. So I need to find the green and the red, the new green and red forces that remained in the left hand side, right? So I have to do a bit of similar triangles. So this is the original triangle, and this is the new triangle now that I cut it at point C. So this is point C, right? This is point C, my new rectangle and my new triangle, and let's just apply similar triangles. So 60 and x and 60 minus x, right? This was the original triangle, and I can write, let me just remove this. I can write 20, right? 20 pounds per foot, right? Where to 15, right? I am talking about this big triangle. 20 pounds per foot were equal to 15, or were to 15, in the same way that x, right? X is to 12 feet, right? I can write that ratio. And then x is equal to 16 pounds per feet, which allows me to calculate 60 minus x as 44 pounds per feet. Just similar triangles, just to get my dimension. So this is 16 and this is 44. And I am now able to calculate my equivalent forces from the left hand side. So this guy is 16 times 12 divided by 2, 96 pounds, and at a distance of 4 feet, right? 12 divided by 3. And the force in the rectangle is equal to 12 times 44 equal to 528 pounds, distance equal to 6 feet, right? So I bring my new forces, right, to my left hand side. And now I am able now to find my internal forces. So working on that left hand side, right? So I'm looking at these forces with this orientation, right? With this orientation. So sum of forces in x equal to 0, right? Immediately tells me that the normal force is equal to 260 pounds. Sum of forces in y equal to 0 tells me that my VC is equal to 649, right? I just have to add this force, and this force, right? Gives me 649 pounds. And sum of moments equal to 0, right? I have a force coming from the 25 reaction, right? 25 reaction. I am adding forces at the very point C. So I have a force coming from the 25 force times 12 feet plus, right? And that is that causes counterclockwise moment, so it's positive. So the 96 also causes counterclockwise moment, 96 times 8 plus 528 counterclockwise moment times 6 feet plus the moment at C, and then the moment at C can be obtained as 4,236 pounds per feet going clockwise, right? Going clockwise. So the nice or the interesting things we did for this example was that we cut through a distributed load, and that changed a bit my forces. And even though I had calculated them before, once I cut them through point C, I had to recalculate my equivalent forces. So this is this example, right? And illustrated quite a few nice things. The next topic, right? The next topic is going to deal with a special type of connection between a beam that is very often done in practice. And then it will change a bit the way that we think about internal forces, because it will very nicely give us another equation, an additional equation we can use. And then we can solve for 4 unknowns, right? Because we gain an additional equation. So more on this on the next video, right? Thank you, and see you on the other side.